Now that you've studied Newton's 3 laws of motion, let's use those laws to draw good force diagrams. We call these force diagrams free body diagrams because we draw an object free of its surroundings and show only the forces that are acting on it. As we've talked about in 1D and 2D motion problems, the key to solving problems is to first have a very good diagram to start with to lead yourself through the problem-solving process. So reviewing our 3 laws, the first law, of course, covers equilibrium, and we have both static equilibrium and dynamic equilibrium. And the key there is once we have our diagram set up, we get to sum up our forces and set them equal to 0. The second law takes over where the first law leaves off. If we're not moving or at constant velocity, then we must be accelerating, and that's where the second law is. And of course, there's a slight change to the equation. The sum of the forces equals mass times acceleration. In fact, many times you'll see me use the second law first, and I'll just cancel out the acceleration to bring it down to 0 if it is in equilibrium of some type. So we'll just show this work. We'll just zero out our acceleration, and typically right next to this 0 I will write either static or dynamic just to let the reader know how I'm solving the problem. And finally, don't forget that we also have the third law. If we have an action, we have an equal and opposite reaction. Keep in mind that we are dealing with vectors. Just like we did with 2D motion, we'll apply Newton's laws in the x direction, in the y direction, and in the end, we'll bring them together to finish solving the problem. Just remember that when I say net external force, there's several other ways we could state this. So net external force is also known as the total force acting on the object, the sum of the forces acting on the object, sigma f, using our Greek letter sigma, the net force F net, and the resultant force. So here's an overview of how you go about drawing force diagrams. And remember, these are also called free body diagrams. And we call them free body diagrams because we draw a simple object free of its environment, and we only look at the forces acting on it and analyze what the motion of the object will be as a result of those forces. And of course, we like simple physics diagrams, so feel free to use a circle, a box, or other very simple shape to represent your object. Occasionally I'll show like a surface of a table or something like that as a light dotted line, perhaps just to give a frame of reference. And typically we'll also put in a weight or mass inside the box. When we're dealing with forces, of course, especially with the second law, we do have a mass that's involved, and that's going to be very important. So here are a few different examples, and this really is a 5-step process we're talking about here. Here's our simple diagram. Now we're going to do step 2, which is label the diagram with our forces. And each force that we're going to draw in here have to touch the box, touch the object. If you don't touch the object, it's not acting on it. That's the way you want to think about this. And I always start with gravity, and in most of our cases, gravity will be acting on an object. And here's another case in the top case. I'm showing you here's a force of a rope pulling upward. We've got a pushing force on the middle object, and we've got a pulling force on the rectangular down at the bottom. Remember that with a pushing force, I could just as easily translate this over to the other side. As long as we keep the magnitude and the direction the same, the force is the same. I tend to like to draw forces pulling an object rather than pushing. Any other vectors that are not forces, we can draw those off to the side. If you take, for example, the top object, let's just say that object is accelerating, and let's say it's accelerating downward. And suppose we have a velocity, and let's say our velocity is upward. If you can imagine that scenario. Remember, if we have an initial velocity and acceleration, and if the forces are constant, that means our acceleration is constant. Therefore, we could use our 1D motion problems in this case to solve for the future position and velocity of this object. So if you happen to know the value of a force, or if you can calculate it, you should include it. The bottom 2 examples, we do have the weights given in both cases. Well, the weight in the middle case and the mass in the bottom case, and we can calculate weights for both, or the force due to gravity to both. So write those values in that you might know. So to your best ability, you should draw the forces to scale so you can help estimate answers to problems and see how close your answers are. Finally, after we draw all these vectors, typically what we're doing is applying Newton's first or second laws, which means we're going to take the sum of the forces. Now remember, if we do have a 2D situation, for example, we have this pulling vector in the rectangular problem, we would have to break down that vector into x and y components. So somewhere in my diagram, as I've done in the upper left corner up here, I will show which direction I'm declaring to be the x and the y directions. Typically we declare positive x to the right and positive y up, but you'll see later I'll more frequently declare positive x to be the direction of the objects moving. So now what I'll do, I'll break down the vectors. Here's my x direction of this vector. Here's the y direction, which means basically I can remove the other vector if I wanted to, because this fpx and fpy are equivalent to my fp vector, my pulling vector. And now you can see I've got two vectors in the x direction, two vectors in the y direction, and then I can start looking at applying Newton's laws in the x direction independently from the y direction. So in the x direction, I could take these two forces, negative ff and positive fpx, and the directions of these tell us our signs, add them together and set them equal to, on the right side of the equation, mass times acceleration in the x direction. If your acceleration happens to be 0 in the x direction, if you're in some type of equilibrium, go ahead and zero that out. Similarly, in the y direction, I could take my two y forces. I have a positive fpy, and I've got a negative fg. I could add those two together on the left side of the equation. And on the right side of the equation, I'd set that equal to mass times acceleration in the y direction. If this box happens to be sitting on the ground and maybe sliding to the right, then I would know that my acceleration in the y direction is 0. And I could cancel that out if I wanted to. And at this point, once you have these equations set up, you can solve for any unknowns. And you'll notice this was the 5-step problem-solving process from before. We drew a diagram. It's a free body diagram in this case, a force diagram. We labeled it with vectors, drew our vectors to scale. We made any assumptions that we need to make and determine what we're going to find. And then what relationships apply? Well, for forces, we're going to apply Newton's laws. We've got Newton's first, second, third law, and later on you'll see we have also a law of gravity that we can use. So now what I'll do is I'll practice 30 different simple scenarios. And these scenarios are designed to give you some practice in thinking about what types of forces act on objects, how to draw them in, how to apply Newton's laws, and to analyze whether or not something's in equilibrium or not in equilibrium. So the first thing we'll do is draw a simple force diagram. And of course, the key to drawing a force diagram is you have to capture all the forces. If you're missing a force, you won't get a right answer to your problem. If we're given a mass, calculate its weight. If we're given values, we're going to label and draw to scale. State any assumptions. And then for each situation, I want you to take a look at it and think about it and just state whether it's in static or dynamic equilibrium or not in equilibrium. In other words, it's accelerating. If you're not sure what it's doing, check off not in equilibrium, because you'll figure out later whether or not it is. And remember, we're actually looking at this in 2 dimensions, so we're going to have to do this in the x direction and in the y direction. So once we've done that, then we can apply Newton's first, second, or third laws and sum up the forces in each direction and see what happens. So let's start with an apple hanging from the tree. This apple certainly is not moving if it's hanging from the tree. Let's assume it's not a windy day. And so in the x direction, nothing is happening. This is not moving left and right. In the y direction, it's just hanging there. It's not doing anything there either. And so we're really in static equilibrium in this case. And if we look at the forces acting, I typically like to start with gravity. And the force due to gravity, well, what is it? Well, we have a mass up here. We can multiply the mass in kilograms times gravity to get our answer. And so let's use this simple equation that we came up with before. And so we have the force of gravity is 0.2 kilograms times 10 meters per second squared, roughly speaking, which is 2 newtons. We'll use the same value in a number of other problems as well. Now we do have another force pulling upward, and that is the tree, the stem of the branch holding the apple on. And that's we call that tension. Like a rope or rubber band would be in tension. We would simplify that as Ft. Now let's apply Newton's first law to this situation. This is Newton's first law because we are in static equilibrium. Here are my axes orientation, and we're going to be using the y direction only in this case. And for the first law, or sum of the force in the y direction in this case, have to sum up to 0. So this is a very simple situation, and you can just look at this problem and you'll know that if the sum of the forces have to be equal to 0, we have 2 newtons acting downward, so we must have 2 newtons acting upward. So this is a very simple answer. If you would like to see how this is done mathematically, as we will do so in more complex problems, let's just do this as a starter. So watch how I do the substitution. You want to follow the same methodology when you're solving more complex problems, certainly. We're going to take our equation. We wrote it down first. Sum of the forces in the y direction equals 0. Later on, you'll see that I'll just assume everything's accelerating and cancel out the acceleration. So I'll just start out with sum of the forces in the y direction equals mass times acceleration in the y direction, and then 0 out ay. But in this case, we'll start with 0 because we did identify it as equilibrium. And so what I'm going to do now is I'm going to substitute into this equation. I'm going to substitute into the left side all of our forces that are acting on this and add them up. And on the right side, I'll just put my 0 in. That's already there. So on the left side, here we go. Let's add up all of our forces. We've got two forces. We've got Ft acting upward, Fg acting downward. We're going to use our sign convention that we defined up top here. We've got positive is upward, negative is downward. So we'll assign our signs to these forces manually as we go through. All right. So we have positive Ft, the plus means we're pointing upward. We've got minus Fg, the Fg, the negative meaning we're going downward. And of course, on the right side of the equation, we'll bring this right side down below here. The 0 is still 0. And you'll notice my note I put over here is if I'm using the mass times acceleration of the y, I would substitute for the acceleration of 0 in this case and 0 things out. If we do a little bit of math here, if we add Fg to both sides, that the force due to tension equals the force due to gravity. We already said that right up front that was the case. So therefore, our force due to tension is 2 newtons, just like gravity was downward. And of course, that's a really, if you think about it, is a restatement of Newton's third law. We've got an equal and opposite reaction. We've got gravity acting downward with 2 newtons, and we've got force due to tension acting upward with 2 newtons. So let's summarize a couple of forces that we've just discovered. We've got forces due to gravity and due to tension. And force due to gravity, don't forget, that's just your weight of the object, and that equals mass times gravity. Typically, we draw this vector first. I like to do that at least. And which direction? Well, down towards the center of the Earth. And gravity is an attractive force. Two objects that have mass have gravitational attraction towards each other, and so it's always pulling towards another object. Later on, we'll deal more with Newton's law of gravity, and we'll use multiple objects, and we'll see how they interact with each other. The other force we saw here was tension. Anytime you have a pull acting on something, we can call it a tension. And that's sort of like an attractive force, you could think about it. Think about a rope or rubber band. If you have a rubber band, you stretch it, it's pulling on both ends. If you have a rope, you're pulling on it on your end, it's going to be pulled on at the other end as well in the opposite direction. The forces due to tension are always directed along the direction of the rope or whatever tension object we're using. You'll see that later on when we have ropes around pulleys. Pulleys are just a nice way to turn directions with forces. Now let's let the apple fall off the tree. How does this problem change? Well, in the x direction, nothing is happening again. In the y direction, we're not in equilibrium anymore. We're not in constant velocity. We're accelerating down towards the Earth. And so we're going to be using Newton's second law. So once again, we have our force due to gravity that we calculated last time was 2 newtons. And we're going to apply the second law because this is accelerating now. And there's our directions that we need to state which way we're assuming is positive. Similar to before we had some of the forces equals mass times acceleration, where acceleration was 0, so we had a 0 here. But now we do have an acceleration, so we will use the second law and plug in. We're going to use the same method we did last time, and watch carefully and follow this methodology. Let's plug in all of our forces on the left side, and we'll plug in any knowns that we have on the right side. So on the left side, we're going to plug in our forces with our signs. We only have one force in this case. That force is Fg, and that Fg is acting downward, so that's a negative sign. On the right side, we're going to substitute in 0.2 kilograms for our mass, and our y, Ay, is unknown. Now let's go ahead and do a little bit of work with this. Let's divide out the 0.2 kilograms to the other side of the problem. So we have negative 2 newtons divided by 0.2 kilograms equals acceleration in the y direction. So if we divide this out, we have acceleration in the y direction is negative 10 meters per second squared. Well, that's not surprising. This is accelerating due to gravity down towards the Earth. Now let's look at another simple situation. We've got a book sitting on a table. Here's our axes. Here's our weight. Our weight is given to us, so we don't have to do any calculations. If we wanted to, we could convert this into kilograms and then convert it into newtons by multiplying that kilogram mass by 10 meters per second squared. And what do we have going upward? We have the table pushing back upward. Sometimes this force will also be called a support force, or sometimes, and more frequently, what we'll be using is a normal force. We call that Fn. And we'll explain in a minute what normal force means. So in the x direction, we have nothing happening. In the y direction, nothing is moving. The object's not going through the table, and it's not flying up into the air, so that's static equilibrium. So what's happening? The object's at rest, so the net external force must equal 0. This is just like the tension case we had in part 1, and using the same methodology, you could do it mathematically, or you could use your logic here. If the sum of the forces equals 0, if we're not moving, then our total force has to add up to 0. So we have 3 pounds downward, we must have 3 pounds upward. We can use either the first or the third law to justify that. So here's our new term for the day. It's normal force. And sometimes, like I said, it's called the support force. And that's the force when two objects are in contact with each other. It's the force that you push back on one object to another. Another way to look at this is how hard two objects push against each other. The normal force is always perpendicular to the surface the object touches. And here's a question for you. How could you actually measure your normal force? Is there a method you could use to measure normal force? If you think about our definitions up above, I'll bet you can find out a way to measure this. Okay, now here's a question. And you know how I love these little questions that are not tricky at all. True or false, the normal force, Fn, is always equal to the object's weight, Fg. And we're talking about the magnitudes, disregarding the signs here. So certainly in this case, we have the normal force acting upward with 3 pounds and the force due to gravity acting downward with 3 pounds. And so the magnitudes are the same. So if you just looked at this problem, you would think it was true. As it turns out, it's false. The question is, can you tell me why? Come up with an example. Moving on, let's take a look at a hockey puck. We've got a hockey puck sliding along the ice at a constant velocity. And we're going to assume that there's no friction involved here. This is like our little hockey puck that I had with a balloon on top of it. So what's happening here? Let's analyze the forces. So here's our directions that we're going to set up. X to the right, Y upward. Start with gravity as usual. Our force due to gravity, I use the same size hockey puck as our apple. Opposing this gravitational force is an upward force. You could either call that the ice acting on the puck, or you could call that a normal force. Once again, the normal force, you'll notice, is always perpendicular to the surface that it's acting against, which is the ice. Once again, we could, just like in problems 1 and problems 3, we could just take a look at either Newton's first and third laws, or do a little bit of math if you'd like, but certainly our normal force is going to be equal and opposite to our gravitational force. So nothing new here. And once again, this is in static equilibrium in the y direction. So what about the x direction? This is moving at a constant velocity in the x direction. So are there forces acting in the x direction? Well, what we can say about the x direction, with constant velocity, this is Newton's first law, we are in dynamic equilibrium, so our sum of the forces in the x direction has to equal 0. That's all we can say about this. There may be forces acting in the x direction. We don't know. There is a velocity. Let's assume it's to the right. And this is going to be in dynamic equilibrium. So our sum of the forces equals mass times acceleration in the x direction. This is an example of how I'll use Newton's second law, but I'm going to tailor it right now. I'll take out the acceleration, set it equal to 0, because we are in equilibrium. So what forces are acting in the x direction? Not sure. We may have counteracting forces here that are canceling each other out. So now let's take the same hockey puck and we'll put it on a wooden floor. This is not on ice. And what you'll do is you'll pull on it with a string, and we're going to pull to the right with 1 Newton of force. But let's assume, even with 1 Newton of force being pulled to the right, it doesn't move. So let's take a look at what happens here. So here's our directions once again. X to the right, Y upward. Gravity acting downward, 2 newtons. Upward we have, just as we did last time, we have our normal force of 2 newtons as well. So those are our forces in the y direction. Let's take a look at the forces in the x direction. We have a 1 Newton force being pulled to the right. And if you look at my vectors, these are drawn to scale. The red one is half the length of the blue ones. What other forces are acting on this? Well, we have to have more forces than this because the hockey puck does not move. With our red forces here, if this is the only force that I had on here, this puck would be accelerating to the right because we have an unbalanced force to the right. So we need a balancing force to the left to keep this from moving. This isn't static equilibrium in the x direction after all. So what is that force? Well, of course, that's friction holding it back. So let's just take a look in the y and x direction. Let's do a little formal analysis here. In the y direction, we're in static equilibrium. We've done this before. We've seen this. So I've zeroed out my acceleration to the y because we're in static equilibrium. And once again, if our sum of the forces is 0, we can use Newton's first or third law, use a little bit of math if you like, or use a little logic, write it down, that these are equal opposite forces. So we have 2 newtons. So what's happening in the x direction? In the x direction, we have static equilibrium. Now the sum of our forces must equal 0 for static equilibrium. As you'll see, more and more frequently I'll just use Newton's second law, and then I'll cancel out the acceleration if it is 0, if it's an equilibrium case. And so I'll set that equal to 0. Now let's go through and formally solve this using some mathematics. I'm going to substitute in for our left side of the equation the sum of all of our forces. How many forces do we have in the x direction? Well, there are 2. And so I'm going to plug those in. Negative FF, I'm going to assign the negative for the frictional force because it's moving to the left. And on the right side, we have the pulling force, which is pulling to the right. That's going to be positive. Those have to equal 0. Like we saw in our first case with the tension on the apple, I'm going to shift the negative FF over to the right side of the equation by adding it, and I'll get FF and FP are equal at 1 Newton each. And of course, that's what you'd expect in equilibrium. You'll have 2 forces, so they have to be equal and opposite. Now let's look at this problem a little bit more. We're going to take our string and we're pulling it a little bit harder, and finally it begins to move. By the way, when it finally begins to move, we find that it pulls a little bit easier. It only takes a half Newton of force to maintain a constant velocity moving to the right. So let's show our x direction and y direction as we do always on these problems. Throwing gravity first, 2 newtons. We've got our normal force of 2 newtons. We've got a force to the right. This time it is a half a newton. Now, we are moving at a constant velocity here, which means we must have another force to the left, which is the same size, to balance that out. And once again, that's a frictional force. In the y direction, we're in static equilibrium, as before. In the x direction, we're in dynamic equilibrium. The last problem, we were in static equilibrium. A little bit different here, but still we have the same forces. And we can add up these forces once again, and we would find that our frictional force is 1/2 of a newton. We've got a half a newton to the left, and we've got a half a newton to the right. And they cancel each other out. We're in equilibrium in both the x direction and y direction. So the new force we're looking at is friction. So remember that friction always acts against the motion of the object. If you're trying to move to the right, it will act to the left. You are moving to the right, it will act to the left. You could also consider air resistance as a form of friction. Whichever direction we're moving in the air, the frictional force of the air hitting against us will always act directly against our motion. We just saw from our 2 examples that there are 2 forms of friction. In our first example, the hockey puck didn't move when we were pulling on it. We call this static friction. If we push an object or pull an object and it doesn't move, friction is holding it in place in some cases. And what we could find, if we added more and more pushing or pulling force to it, eventually it would move when we reach some sort of maximum force. And we call this FFS, force due to friction, static. In the second situation, we found that once we overcame friction, it actually moved a little bit easier. We had a little bit less force to pull. And in that case, we actually had pulled it at a constant velocity, so our pulling force is equal and opposite our connection friction force. But that doesn't necessarily have to happen. We could actually pull faster or slower and actually speed up or slow down. So we call that kinetic friction, FFK. We'll be doing a lab experiment. We'll be doing just that. We'll be pulling objects to explore both the static frictional coefficient and the kinetic frictional coefficient and seeing how those work. Now that we know a little bit about friction, let's slide this hockey puck along the wooden floor and see what happens. Well, of course, it slows down. So it's not in equilibrium in the x direction. So we actually have negative acceleration. So if we're moving to the right initially and the velocity is decreasing, that tells us that we have an acceleration acting backward. It's really important to remember about acceleration that if your velocity is increasing, your acceleration has to be moving with you to cause that increase in velocity. If your velocity is decreasing, the acceleration is working against you to decrease your velocity. So here are our axes, are plus x plus y. Don't forget to write these down. You'll lose 5 points if you don't have these. And once again, here's our gravity acting. Downward, 2 newtons. Upward, 2 newtons. We have our normal force, just as before. We can use Newton's first or third law to justify that. We're moving to the right, and we only have one force acting on this to the left, and that's the force due to friction. That's an unbalanced force. In the x direction, we only have one force acting. By definition, that can't be equilibrium. So it's a non-equilibrium situation, and if we were to plug in to our equation, we have a force due to friction acting to the left, negative sign on the FF. Let's plug in our mass of 0.2 kilograms. Let's solve for AX. So AX equals our force of negative 1/2 of a newton divided by 0.2 kilograms. And we find out in this case that our acceleration is negative 2.5 meters per second squared. Now your job is to come up with nice free body diagrams for the next several scenarios and see if you can figure out what's happening with the object. Is it accelerating? Is it in equilibrium? And try to calculate some values if possible.